Okay, so we are going to start the last lecture on localization. So, and if I can find my stuff, this, well, where do these sheets go? Here it is. Here it is. Okay. So the last thing we want to prove is the following. So we saw that. Do I see chalk? No, I will. A little bit. Some pieces, but no color chalk. So the last thing. So what we saw up to now, right, is that for the Anderson model, at large disorder, typically, if you take, so let me take, so we have h omega minus Laplacian plus v omega, and we can restrict h omega to lambda. I'd be more interested in the finite volume estimates, but so where lambda is just in ZD large cube. So we saw that typically, if you look at the resultant, h omega, so with the lambda, so lambda can be ZD or not, right? Minus E minus I0 inverse NM, right? Typically means for a typical omega and a typical energy in the spectrum, this decays, so you have something like, C n minus m, right? This decays exponentially. Or if you want to be more precise, if we take an average and take a power 1/2 here, we have something like this, right? For C some large constant. We saw the same thing for the semi-group, for the group, sorry, evolution, right? We have the same thing. So that's the matrix NM, matrix element of this operator. We have also that this, and actually you have something better if you take the sup in T, right? This decays exponentially, right? And so what we're interested in now is in transforming this into statements on, sorry, I got a cold. Into statements about the eigenfunctions associated to the eigenvalues. So we already know also that the spectrum is pure point. As I said last time, so on Monday, if you take finite cube, of course it is pure point. Obviously, it's just a finite dimensional matrix. If you take the infinite volume operator, it is also pure point. That's the first theorem that we proved, actually. But we want to say something about the eigenfunctions. So we want to prove the following theorem. Let me write it. So I'll be actually, in my applications, I'll be more interested in the finite volume version of the theorem. So today's goal is to prove the following thing. Theorem. For any p, right, so there exists lambda 0 positive. So the assumptions are always the same, right? The assumptions are the same as in the localization theorem, such that for lambda larger than lambda 0, so at large disorder, for any p positive, right, there exists, actually, you have this, there exists some constant eta positive such that for any p positive, with probability, there exists some q positive such that with probability at least 1 minus L to the minus P. All right, if such that, I forgot something, for L sufficiently large, with probability at least this, if E is an eigenvalue of H omega restricted to lambda L, so lambda L will be, for example, minus L over 2 to the D intersected with ZD. Right, so if you take a cube of side length L, right, for L large, if you take an eigenvalue, then if you take an eigenvalue, then E is simple. So the fact that the simple part I'll prove later on, but is simple. And if phi is an eigenfunction associated an eigenfunction associated to E, then there exists some point x that depends on E, and of course it depends because it depends on E, it depends on omega, right? X equals x of E omega, and it depends in some way on L, as we're going to see, such that if you look at phi at any point x in the cube, this is going to be less than L to the q e to the minus eta x, the distance from x to the point x. Let me call it x sub e. X sub e. Right, and this is going to be true. This is true for any x. For any x in the cube lambda L. So what does it mean? It means that, let me throw a small picture here. It means that if you're giving yourself an eigenvalue E, you can find a point. So I don't draw the lattice, right? But you can find a point x of E such that essentially the eigenfunction associated to E all have, so of course I did say normalized. Right, I take normalized eigenfunctions. All have their weight, most of their L2 weight, inside the ball of size C log L around the energy xe. Right? They essentially live in some ball of size constant times log L around the energy xe, around the point xe. Right? They put all their weight in there. So in particular, they only see the local, they only see the random potential living around them. Right? I mean, the random potential outside such a ball does essentially play no role. Right? If you increase C, the size here in this area, if you look at the, by this estimate, if you look at the L2 norm of phi in the zone which is hashed, right? You see that it is bounded from above by what? It is bounded by e to the minus eta times c log L times L to the q, meaning that if you take eta c much larger than q, q is fixed, right? Once you give yourself an estimate, a p that controls the probability with which you want this to happen, right? The q is fixed by the theorem, and so if you take eta c, so this is L to the q eta c minus q, right? So if you take eta c to be large enough, you can make this as small as you want. Okay? So it means that if you take the c here large enough, really, moreover, the operator is bounded, right? Our Anderson model is a bounded operator. Typically, if the random variables have bounded, the random variables are typically bounded, the operator is going to be bounded uniformly. And so, you see that outside here, you see that an eigenvalue for this, you could, for example, take this as a cube as well, right? It doesn't matter what shape you give it, it doesn't really matter. You could take it as a cube. An eigenvalue restricted to this small cube, right? Or rather said, the eigenvalue of the big cube is essentially an eigenvalue of the small cube, right? Up to an error which is roughly of this size. So if you take eta c large, the error is going to be as small as you like in powers of L. Right? And if you enlarge the cube a little bit, if you admit this cube to be not size log L, but L to the alpha for some small alpha, then you get even exponentially small errors. Right? But what is important is that the eigenfunction only sees the local shape of the random potential. It sees only the random potential near its localization center. Right? Of course, the point x of e is not determined in a unique way. Right? The point x of e is not determined in a unique way, because you see that up to varying the constant eta here, you can change the point in this ball more or less where you want. Right? It will not change very much. So it varies the constants, but that's all it does. So that's the version of the theorem if you work on finite cubes, right? There is a version. As I will not use it, I will not say much, but you can do the same theorem, right? So I can do the following thing. If L is plus infinity, meaning if you look at the cube, at the whole lattice, of course this estimate doesn't tell you anything, right? This is finite, and this is infinite, so it's obviously going to be verified, right? But what you can do is you can do the following thing. You have star is replaced with. So what you do is you use the distance to the center of localization. The distance of the center of localization to 0. You have a constant. You have this. The L doesn't really play a role, but so the thing is, what happens is that 1 minus LP is replaced with 1, right? So with probability 1 now, we have let L go to infinity. And here you have a constant that depends on omega, right? And on, sorry, it's not for, it depends on omega and on p, right? And here you should, yeah. Actually, what you should have said, you can take Q to be P plus D, but okay. C that depends on omega and P, such that if you take here, you must take N X of E to the power. Here you should take P plus D, E to the minus eta X X of E, right? And the important thing is, what can you say about this? And the expectation of C omega P is finite, right? So that's So the C omega P doesn't depend on E and phi, right? So you have to add, there exists C omega P measurable such that you replace omega star with this, right? And you replace the expectation, so this is a random variable, right? Which actually is integrable, okay? So what does it correspond to? It corresponds to the following thing, you see? Now, if you're on the whole thing, what happens is that the cube, right, here there's a norm, of course. This is the distance to 0, right? You can take any distance to any fixed point, but to 0 is fine. What happens is that when x of e goes to infinity, the ball here, over which we control the eigenvalues, or where essentially the eigenvalues do live, is going to be of size log of this, right? That's the difference. Let's say 1 plus. I'm interested in the case when x of e goes to infinity. Okay. So the further away you go, the larger this ball of uncertainty, right? But of course, in the Anderson model, there is no preferred point. We chose this here to be 0, right? But we could have put this point anywhere. So you can do the same thing from any point. Right? But if you want to control for all the eigenfunctions, because what is important is that here we get something for all the eigenfunctions at the same time. Right? So, of course, in this case, you see this estimate here is essentially, yeah, the Q here can be taken P plus D, I think. Maybe P plus D plus 1. I have to check. Essentially, you see that this is the worst possible estimate in the finite cube because, well, x of e, the largest possible, is L, right, anyway. Okay, but the ball gets larger as you look at localization centers that are further away from the origin or from a given point. Okay.
Is it sharp in some sense? Because
it is. It is. Yes, it is unavoidable. It is sharp. I can tell you what's happening. Okay, I can. I give you an example. Wait, that's a good question, actually. Lower bounds. Is it true that you can't do better than that? Right? Well, do the following. Let's take an example. Let's take. Let's do the Anderson model. So we take the Anderson model, okay, and just do the following thing. Of course, this theorem is not proved if you take Bernoulli random variables, right? As far as I know, this is not proved if you take Bernoulli random variables. But for the sake of the example, let's take Bernoulli random variables, just to make things simple, okay? So take Anderson Bernoulli and take V omega at n to be 1 with probability, let's say, P, and 0 with probability 1 minus P. Right? It's not necessary. You're going to see, once you see my example, you'll understand why this is not necessary. But it shows you that you cannot avoid this box. Right? Well, imagine now, so you have a big cube. I'll do it in one dimension to make things really simple. I'll do it in one dimension. Right? But you'll easily convince yourself that essentially the same thing is going to be true in higher dimensions. Okay. So here we have n eigenvalues, so 0 to L. So we have L eigenvalues, right? And clearly, because of this distribution, the infimum of the spectrum of H omega is going to be minus 2D, meaning the infimum of the Laplacian. Right? Why? It's just because 0 here has the fact that all of these are 0, right? All the potential is completely 0, has a positive probability, right? So what you can do, you can use a Weil sequence of test functions that is essentially flat in here, right? And that corresponds to the lowest eigenvalue of the Laplacian, okay? Which gives you that you can find an eigenvalue for this operator restricted to a box as close as you want to minus 2D. right? It's the same theorem. Well, actually, I could just say the following. We proved, actually, I think, in the first or the second lecture, that the spectrum of H omega was the support of this plus the spectrum of the Laplacian. So it's minus 2D minus 2D plus 1, right? We know that. Minus 2D plus 1. Actually, we already proved this, so. But okay. And now, what happens? Well, what happens is the following. So this already tells you, so you want to, now I want to understand when is an, I want to do the same kind of study as in Lifshitz states. When is an eigenvalue close to minus 2D? Right? When is an eigenvalue close to minus 2D? Well, an eigenvalue is close to minus 2D if you have a long sequence, let's say from P to P plus K, with K large. A long sequence where V omega is 0, right? You have a long, so if I draw the potential in this way, I draw here at 0, you have a long clearing like this, where the potential is essentially 0, okay? Because if you have such a long clearing, you can take a test function that is an almost eigenvalue for the Laplacian, okay? Close to its ground state, so actually it doesn't look like this, it actually oscillates here regularly, right? Because the constant function will not give you the lowest eigenvalue, it's going to give you the average of the Laplacian, right? It's going to give you eigenvalue 0 for the Laplacian. Okay, probably normalized. But this one is going to give you the lowest one. Well, actually, no, the constant function for my Laplacian, the way I define, actually no, it's the constant function. It's fine, it's the constant function. Okay, so you have this. And so, if you want to find the lowest eigenvalue, this is what we did with Lifshitz states. What you want to do is to understand, actually it's not what we did with Lifshitz states, but it's close. Well, if you want to find the lowest eigenvalue for typical omega, what you want to understand is, if I take myself a sequence of L independent Bernoulli random variables, what is the longest sequence of consecutive zeros? How large can this clearing be? Right? You want to understand how large can this clearing be? Okay? So if I take L Bernoulli random variables, right? Well, how large is the typical largest clearing? Right? How large is the typical largest clearing? Okay, meaning the typical sequence of consecutive integers such that omega at each of these integers takes value 0. Okay? So let's do the following. Let's take L. So let's try to estimate this. How are we going to do that? Well, what is the probability? What is the probability that there exists a sequence of size L of size K? Here you have only 0. Well, this is probability. The probability that you have a sequence of size K is 1 minus, let me take P equals 1/2. I don't, the P doesn't really play a role, right? So I take 1/2 here. So it's 1/2 to the K, 1/2, sorry. I said 1/2 to the K, right? How many sequences? So the probability that the largest clearing is longer than K. The probability that the largest clearing is longer than K, right? The probability that the largest clearing is longer than K is then bounded from above. Well, what are the possibilities of the clearings of length K? You can take the clearing starting at 0, at 1, at 2, at 3, up to L minus K. So it is bounded by 1/2 to the power k, L minus k. Right? The probability that the largest clearing is larger than k. Right? It means that at least one of the sequence P plus K, or one of the clearings P plus K is made of zeros, right? For some P. You get this upper bound. Okay? And what is the probability that there exists a clearing sorry. What's the second one I want to estimate? What is the probability? Yeah, that there exists. No, it was correct that there exists clearing larger than k. Well, what I do is I just chop 0L into intervals of size, right? K. I chop it into intervals of size k, and I say that, well, the probability that there exists a clearing larger than k is certainly larger than there exists one of these clearings, one of these sequences where v omega is equal identically to 0, right? So it is certainly larger than L divided by k, 1/2 to the k. Okay? And so what you see is that, well, this tells you, hence, the probability that there is a clearing larger than, look at this, what do we take? There is a clearing larger than, what do I need to take? Sorry. The largest clearing is larger than, the largest clearing is larger than, what? Let me say one thing. I need to just want to compute the right constant by hand. Larger than 2 log L is less than 2 over log 2 log L, right? 2 over log 2 log L. This is less than e to the minus 2 log 2 divided by log 2 times L minus K. So it's less than 1 over L.
It's great.
Right, it's less than 1 over L. Okay? I just use this. So here you have K. K is just okay. And now the probability that there exists a clearing larger than, what do I take here? I take, well, roughly the same thing. Larger than, no, sorry, larger than, so I want this time, what do I want? What do I want to? What did I do here? Is this correct? There is something fishy with my second estimate. No, there is something, this is wrong actually, this cannot be true. I mean the number down here is larger than 1, right? So it can be, if k is small, for example, this number when n is large is going to be larger than 1. It certainly cannot be a lower bound for this probability, right? That's just not possible. So what did I do wrong? What I did wrong, of course, is that the events, I should, sorry? Exactly, they can intersect. Yeah, sure, that's what I did wrong. Let me just, I just want, well, what I do is I just do, no, I don't want to do that. Let me think,
We can estimate the probability of complement event.
Yes. Oh yeah, okay, let's do this. Yeah, so this is larger than 1 minus, and so all clearings are of length at most k minus 1, so I take L minus, so I can use this one, right? I can use this one, k minus 1. I use again, right? I just say that the resistor clearing larger than k is 1 minus probability that the largest clearing is of length less than k minus 1, right? And this one is upper bound by that, so I take 1 minus the upper bound. So this is 1 minus probability that largest clearing oh yeah, yeah, that's true. Whoops. K minus 1. So what is the probability that the largest clearing is smaller than k minus 1? So I need to do largest. So the probability that the largest clearing is smaller than k minus 1. So that's a bit painful to compute actually, because I don't want to rule out. I mean, you can sector out by the largest clearing, but I don't want to rule out the thing. Let me think now. What I want to do, I want a simpler way to compute this.
Isn't it a complement of upper probability that largest clearing is less than k?
Yeah, sure. It's the 1 minus. Yeah, this is what I just wrote on the.
No, the upper, not the. This one we wrote already and used.
Yes.
We can change the sign less than k and complement event.
No, because the way this bound is found. No. Just let me think. What I want is a simple computation, because of course you can go to, I mean, all of these things have been studied a lot actually, and well, there are many ways to do that, but I just want a very simple computation.
The probability
So let's do the following thing. I just say the following is that. So I just say that there is a clearing larger than k, right? What I'm going to say is that first this is the clearing which is larger than k.
All other segments have one. You can, for example, you can write that this segment is zeros and all other segments.
No, but what we can do is just the following. This one, right, has only zeros. Then we take this one as only zeros, but we know there is a 1 in this one. Then this one has only zeros, and we know there is a 1 here and there's a 1 here.
Oh.
Then, right, and you sum this way, okay? Because these are all independent, so what you get is that, so you have 1/2 to the k. This is when this one has only zeros, and all of there, we don't care, right? Then this one has k, and this one must have a 1. Right? What's the probability that there exists a 1 in here, right? This is 1 minus 1/2, right? So this is the usual thing. So you choose the 1, so this is k. So it's the binomial law, right? And so you choose this, it's just, I choose the 1 among k, right? And I say 1/2 to the k minus 1, right? What is the probability? Sorry, it's well, no. Let's say it's just 1 minus 1/2 to the k. Right. Better said, right? There exists at least 1, and then you go on like this. So it's just a sum. It is just the sum. So it's 1/2 over k, the sum for k, for p equals 0 to, q equals 0 to p minus 1 of 1 minus 1/2 to the k to the q, right? Because you do it first for 1, then you have the 2 here that are independent, then you have 3 that are independent, and so on, right? So I rewrite this down here. So it is just 1/2 to the k, sum q going from 0 to p minus 1, 1 minus 1/2 to the k to the q.
Why p minus 1? It's a
Because there is, you only go up to this one. Yeah, q is, p is this. It's
L divided by k.
exactly, essentially. P is essentially L divided by k, maybe L divided by k minus 1 or integer part of L divided by k, right? And so this is 1/2 to the k, 1 minus, so I get 1 minus 1/2 to the k. So actually, to the power L divided by k. So this one goes away because it's just the reason of the series, right? Right? So this is to the power p. Sorry, it's 1 minus this. Right? So this probability is larger than 1 minus 1/2 to the power k to the power p. Okay? Okay? And p is of size L over k. Right? So if we want to find that the typical size k, we want this probability to be close to 1. Right? So we want this probability to be close to 1, meaning we want this to be small. Right? So what do we want? This one, k, we assume it's going to be large, right? So we want e to the minus p, e to the minus p, 1/2 k to be small. We want this to be small, right? So what does it mean? It means that we want k again to be of size log L. Right? So So if we take k of size constant times log L, this is going to be a power of 1 over L. And this is going to be L divided by log k, right? It's going to be fine. So this proves that. So this proves that there is the clearing larger than what? Let me do the computation. So again, I'm going to do the following thing. I just take the same. No, not the same. What I want now is I have 1/2. Let me think. Larger than. What do I want? I want this thing. Yeah, I want. So I want 2 log L. If I take 2 log L, what do I get? Okay, 3. I'm going to take 3 log L, right? Let's take, 3 log L log 2, like this. I take this. Okay. What do I get? Then this is larger than what? This is what I said here. 1 minus 1/2 to the power 3 log L over 2. So this is what? This is L to the minus 3, of course, is an overkill, to the power L divided by, so what do I have? I have P over K, so I have, let's say, L log L, right? And I forget about this. I put a 3 here. Okay. Just to get rid of the ones, even a 2 will be fine. I get this, right? And so if I just do the Taylor expansion, let me think. No, I don't want it. Sorry. What do I want? I want this to be close to. Now I'm lost. So I know that I want this to be. Sorry, I want this to be close to 1. So I just take log 2, right? I take 1 over log 2. What I get is 1 over L, right? No, this is still not enough. So I'm going to say that this is 1 over L is not good enough yet. So I'm going to take 1 over 2 log 2. I take this. I get 1/2, right? And now I'm happy. Right, I take 1/2. So here what I do the 2 log 2 power. Right, and now I'm happy because this is exponentially decaying to 0. I changed the thing. I was doing it in the wrong way. I want this probability to be large. I want it to be close to 1. So I want this to be the inverse of something which is much smaller than that, so that the product of the two goes to infinity. Right? So what I do is I do this. I take log L divided by 2 log 2. Okay? If I take log L divided by 2 log 2, if I replace here, I get log 1, I got L to the minus 1/2. This is of size L because it's just L log L. So this thing is smaller than e to the minus L to the 1/2, some constant log L. Right? So it goes to 0. And this probability is close to 1. Okay? So when L is large, you have that the largest clearing is of size between 2 log L divided by log 2 and 1/2 log L divided by log 2. So it's of size log L. Right? So we have that. for L large with probability larger than 1 minus, well, and whatever I have, constant divided by L. The largest clearing is of size contained between 1/2 of log 2, 1 over 2 log 2 times log L and 2 over log 2 times log L. Of course, you can get much more precise estimates, but that's not the point here. The only thing I want to see is that the largest clearing is of size log L, right, times a constant. Well, but now in this largest clearing, right, you can fit such an eigenvalue, right? You can fit such an eigenfunction, right? And what will the eigenfunction typically look like? In here, it's going to look like the eigenfunctions of the free operator. So it's easier in the continuous because in the continuous, we know roughly what it is. It's going to be a sine-like function, right? In the discrete case, you have to modify this. It's not exactly sine-like. But you see that in this clearing, which is of size roughly log L, your eigenfunction is going to be of size, well, the mass is mainly in there. It's going to be of size 1 over log L square root. And it will not decay in here, which is exactly what we saw here.
You say it's not the distance from the zero. You say
No. This is not the distance from the, what I'm saying is that, look, here what we had in this picture, right, is that if you are looking over a bose of size L, you cannot pin the eigenfunction. You cannot say precisely what it is at a better resolution than something of size log L. And this is exactly what you see here. There is no localization center because here the thing is essentially flat over an interval of size log L. It doesn't decay. You don't see the exponential decay over an interval of size log L. Of course, you don't know where this interval is, right? Because you see, it could be anywhere. It's just where the largest, this depends on the sample. I mean, this is something which depends on the omega precisely. But what you can know is that with large probability close to 1, it's going to be of size log L. Which shows that this is essentially optimal, right? This log L here is essentially optimal. So at the bottom of the spectrum, you see that that's something you cannot avoid. Right? Really, these states do exist that live on a rather large portion of space and start to decay only afterwards. And the same thing happens in higher dimensions. Right? You can play the same game with, let's say, cubes in dimension D, and you can exactly the same estimates will yield something of size log the linear size of the volume, but of course log the linear size of the volume is just d times, 1 over d times log of the volume. Right, this is the same thing. Okay, let's prove this theorem now. So what I'm going to prove right now is the fact that it's simple, right? What I won't prove is the fact that it's a simple eigenvalue because this is going to come from another estimate which is called Minami estimate that I'm going to prove, I guess, next time. The only thing I'm going to prove is, so we're going to assume that the spectrum is simple, right? Next time I prove that it is simple. And using this assumption, we are going to construct the eigenfunctions from the semigroup, from what we know on the semigroup. So is this example clear? Right? The idea is really that these log L things do happen. I mean, there's nothing you can do about that, right? And well, one may think, okay, but here we have an example. They happen at the edge of the spectrum and stuff like that, okay? But actually, if you think about it, what you will see is that you can do the same kind of reasoning not only at the edge of the spectrum. Imagine you take a periodic realization of omega, right? Take any sequence of your 0, 1s that is periodic. Okay? Look now at the operator h for this omega. This periodic sequence in your ergodic process of omega gammas is going to appear in the sense that there is going to be as large as you want subsequence that will be exactly periodic, right? Because such a finite periodic sequence here has positive probability to appear. So such sequences will appear. So if you look now at the spectrum, right, of this, you can do the same kind of things, right? You can construct a quasi-eigenfunction, right, a quasi-mode for this periodic sequence. Okay, so it's not going to be clearings anymore, but it's going to be a periodic sequence for which you have this quasi-mode. And you see that there will be modes localized in these things. And the fact that it is, that the thing is going to be, the fact that it's going to be logarithmic, where does it come from? It comes just from the fact that you have repeated many times, you have this period, right? You have repeated this period many times. But this behavior is going to be the same if you have a period, let's say, of 2, for example, 0, 1, 0, 1, 0, 1, 0, 1. It's going to be the same because essentially the 2 nearest neighbor random variables, right, taken together, they behave again as a Bernoulli random variable, except that the distribution is going to be over 4 points. You have 4 possible values, and you get the same kind of estimates. So you see that it's not something which is linked to the bottom of the spectrum. It's something that should occur at any energy. You will have states of this kind. Right? So it's something, this, of course, it's not going to be the case for most of the states. Right? Because most of the states will not come from such periodic sequences and stuff like that. So you can imagine that there are many states which actually we are going to live in things that are, for example, in things that are much smaller, right? And they live over regions of space that are much smaller. But these states occur at any energy level. Right? That's something you cannot really avoid. Moreover, there is a node theorem by Simon that, I don't remember which year, that proves roughly that it's not possible to get something, a constant here, which is independent of L. Right? I don't remember the argument though. I don't remember the argument for this one. But, okay, so let's prove this. So we're going to use the estimate on this semi-group, actually on the group. So we know that expectation over the soup of time of delta m e to the I t h omega lambda delta n is less than e to the minus, let's put it 1 over eta e to the minus eta n minus m. Okay, this we have proved. So the first thing that we're going to prove is that, well, with probability, so this implies, so that's just a very simple argument. So this implies just by the what's called, hence, with probability 1 minus L to the minus P, or with a probability at least one has what? The soup T time e to the I t h omega lambda delta n is less than L to the P divided by eta e to the minus n minus m, right? This is just Markov's inequality. Now I can remember the name of the thing. This is just because the probability that x larger than a is less than 1 over a. So for x positive, E of x. Right, and so the probability, so the probability that the soup is larger than this, right, is then less than the expectation of this divided by that. Okay, so it gives you L to the minus P. That's the right thing, just Markov's inequality. Okay, and the second thing is now we're going to compute the spectral projectors, right? So the second lemma. Let PE be the spectral projector of H omega lambda on the eigenvalue E, right? Then with probability 1 minus, so same proviso as before for any P, for L large enough, L1 minus L to the minus P. One has what? One has that PE, if you look at the kernel of this is less than L to the P, actually, so over eta. I put a constant here. We'll see what constant comes out of computation. N minus M. Right. So, therefore, we're just going to use who PE is. So prove. So we know that by spectral theory, right, P of E is what? It is the strong limit as t goes to infinity of the average 1 over 2t minus t to t e to the minus I es e to the is h omega lambda ds, right? That's just the spectral resolution. Okay. So actually this is essentially through Wiener's formula. And so from this, if you look at the matrix element, so it means that you apply this to delta n, delta m, right? And so you get that this is less than the lim sup when t goes to infinity of 1 over 2t integral from minus t to t. And here you take delta n e to the minus e s e to the is h omega delta m dt. But of course, this goes away. ds, sorry, not dt, ds. This goes away. It's a complex of norm 1. And here we can just plug in our estimate. Right? So actually what we get is that we have the same estimate as here, right? Just the same estimate as we had before. Constant does not get changed. And so we immediately get okay, and now if E is an eigenvalue of h omega lambda. And it's simple. Then we know that PE, the projector, well, it's nothing but you take a normalized eigenvector. But physicists also write in this way. Right? It's just a projector on phi. That's the only thing that it is, if you have a simple eigenvector. Right? And so what do we get? This immediately tells us that phi E of n times phi E of m satisfies the same inequality. Okay. But now, let's take n such that phi E of n, let's take n0 or x of e, sorry, I'll write it x of e, such that phi of x of e is the max. Lambda. Right? But what do we know? We know that the vector is normalized. So we know that this maximum must necessarily be larger than 1 over L to the d over 2. Right? Because we know that the sum of the phi n squared is equal to 1. So if the maximum is less than this, you're going to get that the sum of the phi n squared is going to be less than L to the d divided by L to d, which is less than 1. Okay? So the maximum must be larger than this. Okay? So this is the volume of the cube to the power 1/2. Right? Here the volume, I take the volume meaning the number of points inside my cube. So once you know this, well, you plug this in here and you get that phi E of m is less than L to the p plus d over 2 divided by eta e to the minus eta n minus x of e. Right? You just here we have this for any n and m. Right? We prove that for any n and m we have this. Well, you just take n to be x of e. During the lower bound here you divide and you get this. So you can take q in the theorem. You can take q equal p plus d over 2. Okay. And the infinite dimensional case, I mean, sorry, not infinite dimensional, for the infinite volume, it works in the same way, actually. I mean, except that what you use is instead of looking, so what's the difference? The difference is here. The difference is here, right? Where you want this E of x to be summable. So what you do is you add some summability factor. This is why I had the 1 plus x of e to the power something, right? You add it in here. So, but it works. Otherwise, it works in the same way.
You see, the last this argument about taking max. If you have an infinite.
No, you don't use the max. What you do? No. Of course, here you can also take the max. You can also it works. I mean, you can take the max again, right? Why? It's because this series is going to be summable. It needs to go to 0 at infinity. No question, it's summable, right? And so what happens is that the max is going to be sitting in something finite, right?
But what's about the estimate?
Yeah, the estimate you cannot. But what you use is you don't do it in exactly the same way. The first thing is that here what you do, you don't use this. What you do is that you want something with probability 1, okay? So what you say is the following thing. You transform this estimate into, sorry. So what you do is the following thing. You use this, and here you put some 1 plus, let's say, m to the power, so there's no L, and you put some 1 plus m to the power q. Okay, you want to know this. And here what you have is that this is going to happen with which estimate? Because of this, it's going to happen with the estimate 1 plus m to the power minus q, right? For the infinite case. That's the same thing, it's Markov's, right? But now you can, the bad event, right? Because q is larger than dimension, the bad event is of probability m to the minus q, right? So the sum of the probabilities of the bad events is finite. So by the Borel-Cantelli theorem, you know that almost surely it's the good event that happens, meaning that you have this bound almost surely. Okay, so the first thing is you transform in this bound, you get rid of this one, but you transform it in almost sure bound for this. Okay, this gives you such a bound for surely. Then you carry on the bound here, right? You have the same bound here. You have the same bound. So here you get the same kind of bound with 1 plus m to the minus, so you chose one of the variables, right? M to the power q, yeah? Okay, and here you don't get this, but you have an estimate, and you know that this thing is integrable, right? What you did is you know that this thing is integrable. And now you use this, okay, and now you use the following. The idea is the following thing. If you take, so you have this estimate. If you have this estimate, right? And now you choose m to be the, let's choose m to be the maximum, right? So you have in particular, if you do this with phi xe, you have this, right? And now this is larger than phi of n squared, right? And you know that this sums to 1. Okay, so it gives you a bound on this. Okay, this gives you a bound on what's happening for this one, right? This, you know that if you sum this over n, okay, so it gives you a bound on where x of e is. So let me think. Okay. So what do I want to use here? So what I want is, so I have of x of e. Let me think now.
Maybe we should take maximum of not phi of phi e, but phi multiplied by the same weight, because for that.
No. I think the best. What do I want? I wanted the. Okay, no, what I need to do is I need to replug this into the equation, because you see, what I know, now I want to use this to extract, I want to use this to extract some bound on this, right? I want some bound on this. So what does this tell me? This tells me that the sum this is not, let me think. I want, so,
I again know that the maximum is bigger than not L to the power minus D by half, but by, bigger than this weight, because we need to take Q that this weight is summable in L2, then similar inequality will hold. Yes, and you do the same.
Let me think.
Have a lower bound and maximum, but not in terms of L, but in terms of this weight.
That's correct.
Yes, and you do the same thing.
So what we know, so what do you mean in terms of this weight? So we...
Phi of E, the maximal point is bigger than 1 plus the modulus at the degree Q, because if it's...
Oh yeah.
Maybe to have such inequality we have to take not maximum, but maximum of ratio of E divided by the weight, something like this. Because if an integral of one weight is bigger than integral of another weight, then the ratio is somewhere bigger than 1.
Yes. So we know that we have this. Let me write again, n minus m q, right? So of course we have the same thing if we replace n by m, right? So you could take here, you can do the same thing. You could replace this, but 1 minus n q over 2, 1 plus m q over 2, right? Just by interpolating, right? You do the same thing, replace the rows of n and m, right? And multiply, take the square root, and you get the same estimate for this. Okay, so this is more symmetric. And now what we want is we know that, let me think. What I want to use, but no, this is not good if I... There's something very simple. So again, I'm going to say that let me think now. Okay, what I have, okay, if I take, so the maximum is positive, that we know, right? So one thing that I know is that if I take the sum of c omega squared e to the minus eta n minus xe, so xe is where phi, this one takes its maximum, right? 1 plus, so I take 2 eta here, I take the square of this. So this is xe to the power q, right? And I divide by phi e at xe, which is positive, right? Squared, this sum is larger than 1, right? Because if I take x of e here, I do the division, and I sum this is 1. And I get this sum here, see there's a 2 here, is larger than 1. Okay? Oh no, but this doesn't give me, this gives me just an upper bound on the, I want. No, this is not what I want. What is it? Let me think now. No, yeah, okay, it's much simpler than that. Here it's written, I have this, right? So if I take the square root here, I take a square root and I get q over 2, and that's all. I just need, here I have phi of n, which is bounded by this, right? Well, take the square root. And here we are. And just change the value of eta.
But k over 2 it will not be summable. And
Who will not be summable?
k over 2.
What is k over? Q over 2.
Q over
But that's not important. The only thing I said is that there exists an exponent here, such that if I take exponentially decaying here, multiplied by some polynomial in the size, then I get this estimate. The q is what it is. Q is what it is before. But it's just that this is q over 2. You just take the square root, that's all. And you get it. The only thing is that you lost something in the exponential decay. Never mind. We didn't say what it was, right? I didn't. So that's, just take the square root, that's it.
What is the origin of C omega?
The origin of what?
Of C omega, of the coefficient here.
Oh, this is because what you do is something a little bit more precise than we did. I just said that if you take the quotient, if I take the quotient of the true kernel divided by the estimate, this is going to be a random variable that I know that is integrable. You see, I just said I had in the beginning, I had my, if you want, you have P, E, N, M, expectation is less than, almost surely than, this expectation is less than e to the minus eta n minus m, right? So what I say is that if I take this, I multiply it by plus this, right? And I multiply it by 1 plus n to the power minus q, and then I sum this over m. This expectation is finite, right? If I take the right constant, it's less than, it's finite, right? So I call this thing C omega. This random variable I call C omega. I know it has finite expectation, and I revert the inequality, and I get that this pointwise, it's a sum of positive things. Pointwise, this is less than C omega times that, which is what I say. It's just another way of writing things. Okay? You just use an integrating factor, right? So this makes the thing summable, because here you ate up all the exponential decay. But here the only thing is that you pay the price as you divide. But anyway, when you start with, you do not have the optimal decay. So, okay. So maybe a few remarks to finish this session. So, yeah, the question of what is the optimal decay, right? I mean, is there a lower bound of the same type? That's a question. So here we have proved that in the localized regime. So when, for example, for the Anderson model, when lambda is large enough, when the disorder is large enough, then you know that the spectrum is pure point and its eigenfunctions are decaying exponentially away from some localization center. And then there is a question, so we just have an exponential decay, but this is, well, it's some information, but it's actually very crude information. If you remember the first talk I gave here a month ago about fermions, interacting fermions, right? If you take n particles in the volume lambda, one of the difficulties with this is that you need much more precise information of your eigenfunctions. Imagine you have two electrons, right, inside the system. And you want to understand whether they interact, right? Whether these two electrons do interact. Of course, it's going to be, if you just know that the electrons, their wave functions have tails that are exponentially decaying, there is no way you're going to be able, from just this information, exponentially decaying in this sense, right, just an upper bound, that you're going from this information be able to extract what's the interaction term, right? Even if you know that there's an interaction potential. Because to get an interaction term, to get a real estimate on the interaction, you need also a lower bound. right? You need, because what you want to show is not only that, well, you may give upper bounds on the interaction, but not lower bounds. So it is also of interest to find lower bounds, right? And actually, there is the other problem that I mentioned already in the introduction and also in the talk I gave yesterday. Oh no, last week actually, not yesterday, last week at the probability seminar, is the problem of delocalization. One of the things that you'd like to see is, so this typically is called, this thing, so this coefficient is 1 over a length. This is a length, this is has size a number, right? So this is 1 over localization length. And one would like to understand what is the feature of this, how does this depend on energy? So in the model that we just studied, it doesn't depend on energy. We have this localization length, which is lower bound by a constant, independent of the energy you consider, right? But it is a very interesting question to understand how this constant depends on energy in other models, for example, in the continuous Anderson model, right? And unfortunately, there is essentially nothing known, except in one dimension, right? But even in one dimension, it's not something which is very well known. It's a paper of mine, recent, about a year, well, maybe more, 2013, yeah, so a year or two ago, where in one dimension, one can prove localization using a completely different technique, which is, so in 1D, you can use this as a random matrix, product of random matrices, of 2 by 2 random matrices, right? If you write the Schrödinger equation, you UN equals 0, I write the Schrödinger equation in one dimension. This can be written, of course, as UN plus 1 UN is some matrix Tn of E UN minus 1, where Tn of E is just the matrix. So let's try to get it right. It's the matrix 1. UN we have E minus omega n, 1 and 0, right? And so you can study. So of course, this can be expressed in Tne, T1E, U1, U0. Right? So you can study the spectrum of the operator just by looking at these random matrices as the product of random matrices. Okay? So what these, when omega n change, what these random matrices do is they turn your vector, right, and change its length also. So these are called co-cycles of random matrices. Such co-cycles have been studied a lot, both by probabilists and dynamical system specialists. And one of the things that is well known is that if you look at, take the norm, right? Take the norm of such a product, take the logarithm, divide this by n, right? So these depend on omega, I don't write it. Well, this thing, when n goes to infinity, converges to some positive number, which is called the Lyapunov exponent for this finite difference equation, right? And this Lyapunov exponent is something which is well defined. One can say many things about its irregularity as a function of energy, right, in one dimension. One can show that, for example, the Anderson model can be shown to be always positive. Right, it doesn't vanish. There are other models where it vanishes in one dimension, but not of the kind that we looked at, but in quasi-periodic models are known for which it vanishes and so on. And one can show, actually that's a recent result of mine, one can show the following is that for the 1D Anderson model, for any p positive, same thing as before. So for any p positive, there exists q positive, such that for e eigenvalue of h omega, or let's say on minus LL, there exists a phi associated the eigenvector. Then there exists some x of e in minus LL, such that if you look at phi of x, or phi of x. I write x as an integer variable, I write x. Then this is going to be, for any epsilon, sorry, you fix epsilon. Now let me remember. For any epsilon positive, there exists q and there is an eta, such that here what I have is, actually I don't use q, I use eta. I have the following. I have e to the minus the Lyapunov exponent x minus xe 1 minus, so this one is the upper one, it's 1 minus epsilon. I have the Lyapunov exponent e to the minus gamma e x minus xe 1 plus epsilon. So essentially it is, what you get is, so in the epsilon, it's uniform in this case. And you have a correction term. You have e to the minus eta L. Let me think. No, this is not correct, or it's slightly better than that. No, this is correct. Yeah, you have this. This is correct, but here there is something, no, there is one thing that is missing, because I don't have this for all x's, I have it only, there exists eta of epsilon. It's a function that goes to 0 when epsilon goes to 0, and what you have is roughly, if you want it for all x's, you need to put this error, eta L. Right? So you have lower and upper bound by the Lyapunov exponent. So this thing here, right? This thing, these two things are essentially the same if, so what you can get rid of this. So this is for all x's in minus LL. This you can get rid of if you assume that x minus, so you can, it's another way to state it is that you can take this, and this is going to be valid if x minus xe is larger than eta L. So if the point is sufficiently far away from the localization center, then you both have the upper bound, but the corresponding lower bound with the same exponent, right, up to this error epsilon.
Maybe you have the same bound if you're sitting at the bottom of the spectrum, yes. Does this correction terms appear from sign?
Yeah, they do, but you don't see them because you are only,
Yes, if you're far away, then yes, but can you state something that this function is not far from constant if you are sitting
not in such generality, because this is, what you're saying will not be true in general. These were examples where you have this, but there are other examples where you don't have this. I mean, the thing is that there will be eigenfunctions that look like what I said, where things are like a constant, but there are other ones which will be peaked much more. And I don't know of any theorem that is saying you have one or the other, because I think you have any range in between. You understand what I mean?
Yeah, but you say, so even at the bottom of the spectrum...
No, that's in the whole spectrum. That's not at the bottom of the spectrum. So what I said here at the bottom of the spectrum is going to be true if you are really at the bottom of the spectrum. That's going to be correct. And this you can make a statement of as well. Yeah, indeed.
Yes.
But that was not my point. Here, this thing is valid for all energies in the whole spectrum.
Yeah, I said, but you said I just wanted to feel where does this additional multiplication come from?
Well, it comes from the following thing. If you want this to be true for all xe, you need some multipliers here.
Yes, just because it's not constant. It may be something like
Exactly. It's because the exponential, but it's also because the exponential decay is not exactly this, right? For a given energy E, you see, if you look at this is a limit when you have sent things off to infinity. Okay? But this statement is a statement which is not in the limit. It means here you have this statement for all x's over the thing. So the limiting behavior is not going to be correct immediately at the beginning. That's not going to happen, never, right? I mean, that's something you cannot reasonably expect for. But what this says is that it's nevertheless going to happen not too far away from the beginning. You don't need to be at, you see, the main statement between this and this, the main difference of the statements between this and this is the following thing, is that here you know that it's a limit, meaning that you don't know when you take n how close you are to gamma of e. Here what I'm telling you is how close you are roughly. I'm telling you that if you take n, then you have a small epsilon such that as soon as you leave epsilon times L, you're already close to gamma of e. Right? This is roughly what this says. And the main difficulty in this is the following thing, is that this Lyapunov exponent, so it's easy to show that actually this function, gamma of e, is upper semi-continuous. It cannot jump up, but it can jump down. That's something which is not avoidable. Meaning that the function, right, it can have drops. So if you look at this product, the fact that it's not that the upper semi-continuous comes from the fact that it's the log of something which is roughly harmonic. So it's a harmonic function. It's subharmonic. Sorry, it's a subharmonic function. And so the thing is that what's going to happen if you take your matrix. Here you have a finite dimension matrix, right? You have eigenvalues. So these eigenvalues are just isolated points, right? Discrete points. But this Lyapunov exponent is something over this range. For if you have a matrix of size A, you can define the Lyapunov exponent for all energies that are even not eigenvalues. This is going to make sense. This product, this logarithm, is going to make sense. Right? But what's going to happen is that there will be some energies for this product inside not the spectrum, but inside the interval where the spectrum lives, where this is going to be much smaller than the expected typical size, gamma e times n. Why? Because there will be some special phases where these matrices, imagine, typically think of the following thing. Imagine that this thing is not random, it's periodic. Imagine that it is periodic. If it's periodic, then the Lyapunov exponent can be shown that it is 0. The typical behavior at infinity is 0. But where does this come from? The matrix, the individual matrix here is typically also of size O of 1. But what happens is that when you should think of this in dynamical systems terms. You have the vector, you let the matrix act on it, right? Each of these individual matrices has one direction, it's hyperbolic. It has one direction where it lets the vector expand, and one direction where it contracts, right? What this tells you is that when you multiply many of these matrices, because they are distributed randomly, the directions where they contract and where they expand interfere in such a way that there is still contraction in some direction and expansion in another one. Except that now this direction is going to be a random direction. This is going to be highly random, right? But if you take periodic, then each of the matrices will have a direction where it extends and contracts also, that's correct. But what's going to happen is that they will have non-destructive interference, right? There will be no rotation. So they go always in the same thing, in the same direction. And so this may happen over a period if you take here a special energy, it may happen that you're again in the same case. In which case, you don't get any increase of the Lyapunov exponent for a certain number of n's. When you multiply on the product, it doesn't increase. But because you divide by a large n, this number goes down. And then it goes up again. But this depends on the energy. That's something which is very energy dependent. And the whole difficulty in proving this theorem is to prove that when you look at the very special energies that are eigenvalues of this operator, this phenomenon does not happen. You see, because you'll have, when you look at the finite, if you look at just this thing, this depends on omega. So that's a random variable. So the points of the energies where the thing has this non-typical behavior is going to be a random set. Okay? And the difficulty is in showing, but of course, because this and the eigenvalues depend on the same omega, it's going to be non-independent of omega. And the difficulty is to show that the points where bad things happen for this product are not the ones inside the energy spectrum of your Hamiltonian. Right? Okay. But anyways, in one dimension you can prove such a thing, and actually you can prove such a thing for much more general models for the Anderson model. This is not written up yet, but it's pretty clear from this proof that it's going to work, right? The idea is going to be the same. So I think that's the first instance where you have actually, where you know first that you have a lower bound and you know what's the rate of decay, right? You have an actual estimate on the rate of decay for this thing. In higher dimension, nothing like this is known, right? Inside the spectrum of the random operator. What is known is outside of the spectrum. So there was a theory which was developed by probabilists, which is, they also call this Lyapunov exponents, where where they studied essentially, you take minus Laplacian plus V omega, they took Poissonian V omega, and you assume that V omega is non-negative, and they looked at minus Laplacian plus V omega plus E when E is positive. So if you want minus E, and they looked at this. So the spectrum starts at 0 for this operator. And they looked at the size of this green. So the Green's kernel, of course, is you have E that's down here. It's nicely and well defined, right? You are in the resolvent set of the operator. And they looked at what is the, so they showed that the typical behavior of this is some gamma of E x minus y, for x and y large, of course, right? This is typical for x and y large. And they studied what this looks like, right? But it's below. So they don't have anything inside here, which is going to be much more complicated, right? Because the thing changes sign, and it's going to be a completely different story. And it would be very interesting to have something about the localization length in here. But there is, to my knowledge, nothing is known about this. This is just something which, well, except in one dimension. But so one may think that actually one has a good descriptions of the eigenfunction of the localized state, but actually it's, if you think about what you can do with it, right, like interacting electrons and stuff like that, the description is not worth anything. I mean, it's much too crude to give you any reasonable information. And in dimension 1, you can use other things, but in dimension higher than 1, these are really hard problems in analysis, actually. So there are lots of things to be done, really lots of things to be done on this. Okay, well, let's stop here.